I'm very happy and glad to be here. And I'm looking forward to share with you my last 6 years of developing new technologies. As engineers, we always look for something new, something different, something that maybe somebody has not done before. And that's what I'll present to you today. And hopefully I can motivate you guys to understand the challenges, what's ahead of us, and the great opportunity to actually be part of a new and at the same time very old technology. Okay. So shaping the future of RF wireless power transmission. RF wireless transmission, it's new in a sense, and it competes with inductive technologies. It's as old as wireless communications, but I'll tell you more about how each one of them have evolved over the years and how each one can piggyback on each other and move forward. But before I do that, I thought it was important to share with you a little bit of my background. So I put together this one slide that tells you about my experience. I started working in research, applied research for that matter, at Bell Communications Research, which was the arm of the Bell system. I was there for a number of years, about 8 or so, doing fiber optics development, some of the early ATM SONET systems that today are part of the fiber optic networks around the world. I decided that applied research was beautiful, but it was time to start building some products. So I went to NEC, which is, as you know, a Japanese company, and joined their advanced research lab, systems lab. And interestingly enough, they asked me to look at wireless. So I didn't have much of a background in wireless. And that's when I started getting interested on that. And after 4 years of working on 2.4 and 5 gigahertz systems, that went all the way up to 20 megabits per second right around 1999, which by the way was very fast because 802.11 was at 11 megabits per second. I said to myself, well, it's time for us to, and my family of course, to move to the West Coast and see if I can contribute and use my knowledge to now put together real products that can be used by consumers. I wanted to be proud to walk into the store and say, hey, here's my technology, right? And I ended up working for Broadcom. I ran their wireless development for a number of years, was responsible for their single 802.11g chips, the first MIMO 2x2 systems, and deployed that. I then got a phone call from Marvell, a great company. They just recently changed the logo. I was there for close to 8 years and was responsible for all connectivity, wireless connectivity that is. And I was able to have exposure to different wireless technologies. Now, having said that, I was approached by Energous about 6 years ago, and that was an opportunity for me to merge my knowledge of doing research and putting together products. Now, as far as my background on the right-hand side, I've actually supported a number of customers all throughout my career, especially at Broadcom and Marvell. And you will see Samsung there. And I actually have a collection of systems myself. So here's your Samsung Galaxy Tab 3. That's part of my collection. So I keep that as where basically the wireless combo chip was designed by my Marvell team. Similarly, I have some Samsung phones, middle phones, and so on. I worked on Apple products, Airport Express, their air-based laptops, HP products, so pretty much access points, as well as laptops, which is the early Wi-Fi. Had about 75% of the enterprise market with Cisco, about 100% of the Wi-Fi market with HP. Went into Google products, where the Marvell chips provided the Chromecast and the support for Chrome-based laptops. And I think the one that my children are most proud of is the fact that I could bring home sometimes testing devices for Microsoft, Sony, and Nintendo. So gaming devices were all pretty much supported by my team and myself. So having said that, you would go and say, well, Cesar is really a wireless communications guy, and I am, and I've done that. But wireless power is different. Wireless power is not the same. And hopefully today I can explain to you and motivate you to to understand the complexity of it and what's left ahead of us. Okay, so as part of the presentation, I will give you an overview and try to describe what the problem is. I will tell you in a story manner as much as possible what the thoughts were and what were some of the questions that we put together and looked into when we decided to build the systems, what technologies we consider, and most important, what the regulatory challenges were. As you all know, you can build any technology you want, but if you cannot get it certified and you cannot make it low cost enough to actually penetrate the market, it will be almost impossible to gain any traction. After I explain the challenges, I will give you some background of how those challenges would transform into prototyping systems that actually show that wireless power transmission is possible. And once we had those prototypes in place, we were able to identify markets, we were able to identify the technologies, and we developed a system that I will describe to you from a technical point of view today, and I'll eventually give you a demo before I go into Q&A. Okay, so let's start with the overview. You all know that the world is changing. I remember not long ago, 25 years ago, that or more, those that grew up in the 60s and 70s like I did, that we didn't have cell phones, and communications was about the TV, the radio, and the fixed phones. So we were hooked up to the wires. And over the years today, we are no longer dependent on wires. But the difference between 40 years ago and let's say the last 15 years is that we've become animals that are now accustomed to different gadgets. On the left-hand side, you see people at the airports, something that we do all the time, trying to recharge our devices, right? And then on the right-hand side, there's so many gadgets now, and we depend so much on them, that has changed the world even more than before. And why has that happened as opposed to what wireless communications versus wireless power is that in the case of wireless communications, we needed that from the beginning. In the case of wireless power, as long as we had a cable for many generations, we were happy. But now that we have batteries, and batteries are all over our gadgets, and we want instant power to our gadgets, we don't like to be plugging in, that opens up a new opportunity to now develop new technologies and plan the future like we did with wireless communications to start building and evolving the wireless power system. Okay, so again, on the right-hand side, plenty of opportunities. There are phones, today there are smart glasses, hearables, gaming devices, portable computing, home IoT, and this is not all of it. I mean, there's way much more than that. But just these basic ones that I'm showing you today is more than enough to make a case that it's time to do something about it. And I'm not saying that nothing has been done about it. Something has been done about it, and we'll talk about that. And in fact, Samsung played a key role in that. So our world is very messy. Our world is full of wires. I'm sure that every one of you has a box full of these chargers, and you're tired of it. You don't know what to do with them, and they're confusing. You don't remember if I buy a Samsung phone, whether this charger is that charger, and so on. So we want to get away from it. And as a society, we have introduced today inductive-based systems, and I call that, for simplicity, wireless charging 1.0. So the requirements to charge our batteries, to have our gadgets always charged, has pushed us now to develop, if you want to summarize it, and I guess Qi gets to win here, and Samsung gets to claim a lot of that winning, is that we now have what we call wireless charging, and we're all happy. We don't have this unique wire-based chargers, but what we have is we have a transmitter that is inductive. That transmitter, let's say in this case, charges our phone. And yep, it is wireless because it doesn't have a wire connected between the transmitter and the receiver, but it's, for those that are purists in the wireless world, this is called contact wireless. It's not really at a distance wireless, okay? So now that we have inductive power, We go out there, we have our phones and other devices, we have cheap charger pads that are all, again, inductive. We have our electrical cars that are extremely high power. There might not be a one-to-one correspondence on the technology or not. It might be separate or the same. So there's different choices. Things have not converged, and we need to converge. So this is an opportunity for now to go and figure out a way to come up with a new evolution, or call it a phase 2 or a wireless charging 2.0 solution to what we have today. And again, I want to give a lot of credit to the inductive guys and the wireless charging guys to do that. But reality is that customers and the demand is growing, and customers now become pretty pampered, and they just don't want to have one-to-one systems. They want to be able to have one-to-multiple systems. They want to have one transmitter. They don't want to have multiple transmitters. They don't want to have multiple connectors. They want to be able to send power to multiple devices. They want to be able to move them around. They want to be able to do that on the go as much as possible. So that's what we call now wireless charging 2.0. And the vision on wireless charging 2.0 is to effectively be able to charge devices on a wireless basis. And I know that lots of you are probably thinking, it's going to be very lossy. And yes, it's very lossy, and I'll tell you more about that later. But it's become such an important requirement that even the FCC is behind this effort. And if you look at below, you'll see that Michael Ragley, who's a FCC commissioner, recently at CES this year, actually made a very, very important quote where he sees wireless power as a vital and a need to be successful in the future. So once more, we have generation 1, we need to move forward. So how do we move forward? We move forward by having distance. We move forward by looking at the right-hand side of the slide and saying, I can deploy devices that I can somehow charge in front of my computer, call it a personal area network. And there's plenty of gadgets that I'm sure you guys will not mind not connecting and just getting charged as we go. We can go into industrial sites, and we can start powering multiple IoT devices and build cloud-based systems that allows you to gather information while they're being wireless charged. We can go to the store on the right-hand side and have labels that show you on the fly the price of the products that we're buying, right? And even if possible, send you coupons and show you that things are moving. So the world is changing. The world is moving in this direction. There's no going back. But if we stick to the current technologies that we have today, there is no technology yet that can do this besides RF wireless power. And again, it has its limits, and I will talk about that. And on the bottom line, you will see now being able to deploy even military and tactical equipment and so on and move forward. So we're looking at a future world where we'll be able to have our devices charged using RF power, and a world where you can actually have power on demand, if you want to call it, or what sometimes I would call personally quality of service power delivery. So I'm copying, if you guys notice, a lot of the same words as wireless communications because we don't have them, and I have to piggyback on something that I know of. Certainly, I'm sure that as we move forward, some of the words that I'm using are going to change, and somebody will be smart enough to come up with something better than me. Okay? Now, how is this going to happen? This is going to happen by uniting and finding a solution that allows us to come together with a network where we can put all these devices, all these gadgets together and control that via a cloud system, let's say. And just to give you an idea why this is important, just to tell you why there's a market need of this, there are 5 billion devices that need to be connected. And again, these are only the devices that I'm showing you on the screen. I'm sure that I'm missing like 3x those numbers. So there's a business case. There is a need, people's need to make this happen. Okay, so that's the case to actually go and move forward. Okay, and how is that going to happen again? It's going to happen in an evolutionary manner. It's not going to happen overnight. And this is very similar to every other wireless technology that we have developed in the past few years, right? We start by developing technologies that are near field or contact, okay? We want to have devices that we can, that are small and we can take with us in our pockets or in our briefcases, right? We want to then be able to expand those into what I would call a wireless personal access network. Let's say, let's call it for this case, a 1 meter, up to 1 meter. And I call this a midfield transmitter. And then we want to go into far field. We want to be able to go up to 15 feet or more. So, and again, this is going to happen over time. We will go from, again, less than 0.5 centimeters, which we call near field, somewhere between 0.5 and 1 meter, which is where what we call midfield, and up to 15 feet, which is what we call far field. And these are nomenclature that we had to come up with because we did not have at the time when we started working on this a way to define some of these concepts. But this concept is a very important one, so keep that in mind. There's near field systems, there are midfield systems, and there are far field systems. And how you define far field in the future, or how you define midfield in the future, it's all up to us to change and make it happen. So now that you understand what the problem is, what we're trying to do here, I will explain to you what some of the challenges. Some of you might go and say, well, RF is lossy. We're not going to make it happen. And in fact, when I started working 6 years ago, I'll tell you a story. I had some well-known professors that called me that I worked with in the past in wireless, and actually told me that I was crazy. I was going to do something that was abandoned a long time ago. And if I wanted to get 1 watt of power, I would need a receiver maybe the size of a wall in my room. And I listened to them, didn't say much. And I went back and put together a team, and we worked on solving the problem. So I wanted to share with you some of the questions that we ask ourselves, which are relevant to any type of applied research system and any other wireless technology. And this is how eventually we arrived to what I'll show you today. So let me tell you about systems, technologies, and regulatory challenges. So when we basically had to build this system, we knew that we wanted to have an at-a-distance technology, but we knew that we needed to also support contact. So that was one fundamental requirement. How do we build a technology that can be scalable, that can move from contact and also support distance technology? So we thought about that. We arrived to, okay, we're going to do wireless RF. It does make sense because of multiple reasons, which I'm not going to explain right now, but it will become very obvious as I go through the presentation. There were no standards. The only standards we knew of were inductive standards. And we looked at them, and some of it made sense to adopt or piggyback on, especially the communications requirements between transmitters and receivers, which we had to extend because now we were not doing a contact system, but we were actually building at a distance system. And the moment you go at a distance, power transmission, you also have to now use, of course, wireless communications, right? And we, in our particular case, decided to use BLE. We're not constrained to BLE. We can do other technologies, but that's pretty much the thinking here. Now, what kind of an architecture? Gosh, that was a tough conversation. That was a tough conversation because we had three fundamental requirements. We had near field, we had midfield, and we have far field. So how do we build a system that can actually use fundamental, call it Lego block systems, and at the same time being able to reuse and simplify building those in an evolutionary manner? And I will show you today an architecture that we have developed technologies for that kind of answers some of those questions, and I will point out its functionality as I go along. I think a very tough question, and I'm sure a lot of you are thinking, gosh, what kind of a frequency do I use? What should be the right frequency? And the way we looked at this question was, okay, well, we really want to piggyback on ISM. We want to get away from the headaches of having licenses. We want to be able to follow what has been done out there. But should we use 2.4 gigahertz? Maybe. Should we use 5 gigahertz? Should we use 900 megahertz? Should we go and use maybe 24 gigahertz? Maybe 60 gigahertz, or maybe we'll go back all the way down to 40 or below. And reality is that ISM is fixed. So we looked at the ISM band and we identified what we believe was the best frequency. And the best frequency is kind of an interesting answer, because all of those of you that are wireless engineers know that as you go higher in frequency, the distance goes down. As you come lower in frequency, your distance goes up. But as I go higher in frequency, my antennas become smaller, but now I have less distance. And as I go lower in frequency, then my antennas become extremely large. And of those of you that believe that antennas should be at 1 lambda, gosh, I mean, go at 900 megahertz and your antennas are like 30 centimeters long. So we had to actually find a middle ground that also had to take into account health issues. And I'll talk more about in the next slides. Now, this next question was, okay, what kind of an efficiency can we achieve? And that was probably the trickiest, the most fundamentally, the most practical and the most cost-effective question that you can ask for any wireless power engineer. Efficiency translates into being able to transfer as much power from a system out of the system into the battery. And the reason I state this problem this way is because thermal performance is important. Thermal performance, especially as you go up in power, translates into heat, and heat melts. And those of you guys that are experts on phones know what I'm talking about, or laptops, and we actually want to minimize the heat as much as possible. We want to be as efficient as possible. But this is a contradiction. It is a contradiction because you're now talking about RF, you're talking about wireless transmission. And those of you know that Freeze formula is very straightforward, and Freeze formula will limit what you can do. So you might go and say, well, I have Qi and it's extremely efficient, but it's a contact. So it is possible to do high efficiently systems using contact technology. But the moment you go wireless, the moment you want mobility, or call it movement, freedom of movement on your technology, the moment you go into wireless, I mean, there's no good solution today that goes around freeze. And that opens up a tremendous amount of innovation and hopefully in the future, new ideas along the lines of digital signal processing and others, right? For today, we focused on beamforming, and beamforming is one way to recover some of the losses. But the problem with beamforming that we noticed, and I'm not saying it happens all the time, is that as you go into smaller devices and the frequency is high, and you build an antenna array, that antenna array gain is a function of the separation and the isolation across the antennas. And typically you want that to be in the order of 1 lambda. So at that point in time, it becomes really difficult to go and build a 900 megahertz 1 lambda antenna array. Okay, and I'll show you some efforts we've done also on 5 gigahertz. But then we developed systems that allow us to do beamforming. We looked into that. We also looked at non-beamforming, and I'll explain that to you. But wireless power technology is not just about efficiency. It's about convenience. It's about practicality. It's about cost. And today, I don't see anybody ever coming to me and saying, hey, your Wi-Fi, your Bluetooth, or your 5G or your 4G is burning so many watts on the base station, or 15 watts, let's say, on a Wi-Fi access point. But the amount of power that we get is very tiny, and it's so inefficient, so we shouldn't be using it. And that happens doesn't happen at all. But when we go and talk about wireless power technology, I hear the green people saying, oh, God, I mean, we have to be so efficient that if we're not efficient, then there's no way to be able to do this. Well, let's get all together and solve the problem, right? Because if that's what we demand from wireless power technology, maybe we should go and demand that from wireless communication systems too. They're extremely inefficient, but we're all happy and we all have them at home. And if it wasn't for that, especially with this pandemic today, we wouldn't have ourselves and our kids working from home. So there's something to be said there that convenience and practicality is more important than efficiency, okay? We also looked at the technologies, and this was an interesting part of the problem. I'll tell you, it is possible to build a wireless power transmission system using off-the-shelf components. I dare you to do that. You'll have a lot of fun. It'll be an interesting problem to have. But the reality is that all those components that are off the shelf have been designed for wireless power transmission systems. They're not specifically designed for wireless power transmission. Also, their cost is not the right cost. So what we looked at is how do we come up with new designs, new circuitry, new ways to develop semiconductors independent of technology that would be as efficient as possible, as low cost as possible, and be able to also make them scalable and use that technology to build our transmitters, to build our power amplifiers, to build our receivers, and any other part of the system that's required for wireless PT. So our focus was to develop wireless power technologies from scratch using our experience on wireless communication systems. Now, those of you that are antenna guys should be very happy about this new direction in technology. Antennas are a fundamental and important piece of the whole puzzle here. And again, you'll come and tell me, well, if you're going to use 900, your antenna is going to be 0.3. So if you build an array, you're not going to be able to fit this anywhere. Your gain is going to be bad, blah, blah, blah. And that's not true. And I'll demonstrate that today. But it opens up a new set of new way of thinking about antennas. It opens up an amount of research and being able to build different types of antennas, whether they're patch antennas or Yagi antennas, or you call it antennas based on just copper plate, and you can actually go crazy and start building antennas that are actually designed with very, 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 very high decay material. Okay, so there's plenty of work to be done there, and we actually built a number of antennas ourselves and evaluated them at different frequencies, and we have a full library of different antennas that are important and we use today in our development. So those of you that want to get interested in that have antenna background, this is a great way to actually use your expertise. And interestingly enough, if you remember, I talked about near field, I talked about midfield, I talked about far field. Near field means any region in front of a transmitter that it's less than a lambda distance. And at that point in time, the definition of antenna gain is no longer viable. There's no longer an antenna gain, because antenna gain is a concept defined for long range, far field. And the systems don't actually follow those rules. And you will see that because of that, some of the rules that standards bodies have put together for wireless, that's no longer no longer support what's required for wireless power. So we need to go to the standards and make changes. And in the near field, we typically talk about coupling performance, the coupling of the transmitter versus the receiver. And that's when we see the loss. Again, we don't talk about gain there, okay? And not to actually disregard, but putting the systems together and the amount of software development that is required is extremely high. And those of you that build systems understand what I'm trying to say. There's no technology today that cannot be designed top down like we have. You need to have software. Software is the glue. Software allows you to have an out-of-band communications channel. It allows you to control your devices. It allows you to calibrate your devices. It allows you to control your antenna arrays. And it allows you to have a closed system and full control from transmitter to receiver, as opposed to, let's say, other inductive technologies that don't have a closed loop system. And because of that, they might suffer from thermal issues, which we can control very close in an RF-based system. Finally, there are other problems that the software will allow you to do in combination with the hardware that we need to take into account, and that includes sometimes foreign object detection. You don't want to put in anything in front of the transmitter and turn it on. You just want to turn it on when you actually recognize that you have receivers that are wireless power receivers. Okay, so there's a lot of thinking going on. And again, don't think that my list so far has everything that you need to think of, but these are some of the things that I was remembering over the couple of days that were kind of a headache, and I thought was important to share with you, so that you appreciate how much thinking, how much work we've done developing this. Finally, as technologists, we're all happy and we have the technology and the technology works, but we need to make a product. And there's no way that we can actually sell any technology unless, of course, regulatory passes and we have standard, okay? Now, when we talk about regulatory, there are so many different bodies that we have to work with that we decided to actually have our own regulatory affairs team. And we looked at ITU and we continue supporting ITU today, where we are looking at 900 megahertz as a future technology to be supported. And 900 is an interesting choice, not just because it makes sense from a performance efficiency point of view, but it's also interesting because it piggybacks on other technologies like, let's say, RFID, which use very narrow channels. And they haven't percolated as much as, let's say, Wi-Fi or Bluetooth, where they have pretty much proliferated its deployment into the 2.4 and 5 gigahertz bands. Again, I would not use 2.4 and 5, not just because of Wi-Fi, but it's got its own issues when it comes to being health safe or not, and some limitations that we wanted to avoid also. And most important is that cost goes up. And yep, there are some people talking about 24, 60 gigahertz. I wish them good luck. I think that will eventually happen. I don't think it's going to happen anytime soon. Those that work on 60 and 24 gigahertz know the cost and complexity of actually using semiconductor devices to achieve that, and the cost of packaging and so on. So our goal was to come up with a low cost solution. And I think 900 is a viable solution right now for the second generation. We had to interface with a number of government offices. And certainly there's the European office, there's the office in China, there's the office in Korea. For this presentation, I'm just gonna tell you the FCC, and the reason is because we focus a lot with the FCC. And our first approach was, how do we send power over the air in a safe manner and in a legal certified manner? And we looked at PAR 15, but once more, PAR 15 was already limited. Those of you that participated in PAR 15 will probably remember back in 1995 that using 2.4 and 5 gigahertz at 1 watt was a killer. People were afraid to go to 1 watt, and today that's a standard. I remember people telling me, oh, Wi-Fi, Bluetooth is never gonna work on a plane because the plane will go down. Well, that's not true anymore. What happened? Again, some people like to talk about somebody else's work. I suggest that before people do that, they do their homework and figure out why they're saying what they're saying. But PAR 15 is a very nice start, and we did that. It taught us a lot. It taught us a lot about limits. It taught us a lot about how to go around the standards and use the standards to have a wireless power system. But it would not allow us to have distance, even though wireless communications allows for distance. And the reason it didn't allow us to have distance is because PAR 15 is written in such a way that it talks about information being sent over the link. And we were not sending information, we were sending power. So we looked at PAR 18, which you guys know of, and everyone has a microwave at home. And we looked at it and we said, oh, this looks perfect. But PAR 18 requires to have an enclosed system. And it doesn't talk about distance. It talks about localized power. And until we showed up in the picture and we had a discussion, PAR 18 could not go beyond 0.5 millimeters or so. So our challenge was, how do we put together a system? How do we come up with a technique? And how do we put together a process by which we can extend and open up the wireless power transmission standards? And we did that, and I'll present to you part of that. Finally, things are moving forward today. I'm glad to say that. The FCC is very open, and there is what's called an NPRM, which is a new proposal to make amendments to PAR 18. And we are basically setting up ourselves to have together the world's first wireless power standards. It will allow us to refer to a very, very fixed procedure, as opposed to what we've done so far, where we had to go around, and I'll show you what we ended up with in a few slides. And finally, on the standards body, yep, we don't have standards, but we have joined the Air Fuel Alliance. We have opened up our knowledge to everyone and those of you that want to be part of this. There's no way that this will happen without the support from the industry, but we had to do it, because if we didn't do it, there was no effort. And I think we have now gotten to a point where we've seen a lot of interest, and certainly we continue working with ETSI and ANSI and so on. And again, I'm just showing you here 6 different entities. There's more than that we deal with every day to make this happen. So those are the challenges at a very high level. That's what we have to live with so far. So now let me start with the fun part of the presentation. Let's talk about why. Let's talk about how. So let me start by why. Why means background. It means, first of all, I just want to remind you, I'm not talking about inductive. I'm talking about RF. I'm talking about power at a distance. That is the fundamental premise here. I don't believe that anything that has no distance will be a second generation system. So given our background, we built in 2015 a 5 gigahertz based system. And I wanted to prove to this person that told me that what will require a wall, the size of a wall receiver, that wasn't true. And if you look at this slide and you see that room in the back, there is a transmitter. It's an antenna array system running at 5 gigahertz that has proprietary first generation devices that we design in-house here at Energous. It has specific optimized antennas, Yagi antennas, that are in the order of 9 dB of gain or so. And they come together on an antenna array that is a little bit less than lambda, and we were able to control the isolation and almost get the full gain of the antenna. And it is possible to now, having multiple antennas, send enough power at 15 feet to actually get a 1 watt amount of power at the receiver that's mounting there on that rolling table. So those that didn't know said it would take a wall. Well, 5 years ago, we showed that that wasn't the case. Now, we, as a proof of this work, we went to the UL and we asked the UL to do some measurements for us and put together a report. And there's a report we have in-house that shows that, in fact, it is possible that wireless power technology does work. Certainly, a number of questions showed up, and I'm sure a lot of you are saying, oh gosh, I don't want to be in the middle of that. And I agree with you, you don't want to be there. But I'll tell you how to make it happen to be there. So some of the questions that we ended up with is, how do we develop a next generation system where our device is optimal or not? Was CMOS good enough or not? Should I use some other technology? We looked at the antennas and said, we did not use off-the-shelf antennas. Again, don't buy off-the-shelf antennas. You're wasting your time. Go get your best engineers and ask them to design new designs that allow you to do wireless power transmission. We actually can send high amounts of power, but we're also wasted high amounts of powers. I mean, we're talking about hundreds of watts on the transmitter. So if you look at my research background, what we build is really a research prototype. But in the evolution of technology, you do need to do that, because that's how you learn. And we were able to identify this. We looked at all the regulatory concerns, and we were able to come up with techniques and piggyback on previous knowledge to be able to define power at distance. And eventually we came up with very, very clear rules by which we could potentially propose a standard. Okay, so this is 5 years ago. Yes, you can send as much power if you want. And by the way, our devices are so scalable that if you wanted to multiply that transmitter as big as you want, just please go ahead, but just don't ask me to be in front of it. Having said that, I wanted to go back to this slide. I want you to remember this, because this is going to be important as I move along in the presentation. We looked at an evolutionary step. We looked at near field, we looked at midfield, we looked at far field, we looked at near field, less than 0.5 centimeters. We looked at midfield, somewhere between 0.5 and 1 meter, and far field up to 15 feet. Now, if you remember this, that's a good start. Again, there's no definition. That's our definition based on our knowledge, our learning, our feedback from customers, and most important, our roadmap. So what we see is the following. We see on the y-axis the received power, okay, and we're focusing on all the way from very low power up to 40 watts or so. Then we're looking at the x-axis where we're looking at distance, okay? And then based on the feedback from customers, what we did is we looked at the upper part of the slide, and you'll see near field, you will see midfield, and you will see far field. So near field less than 0.5, midfield up to 1 meter, far field up to 5 meters, which is around 15 feet. And I did not mention this, but there's also an effort on harvesting. And harvesting, from our perspective, can be of two types. Can be, call it a passive harvesting, where you're trying to pick up any type of RF wave out in the environment, which, by the way, is not going to give you much. And if you have an extreme low microwatt type of sensor out there, you might actually be happy with it, because you're just charging your battery so that you send a blur of information once every so many days or so. But what we've been looking here with my team is looking at actually active harvesting. Active harvesting is where you deploy well-known devices, transmitters, and in my particular case, cloud-based systems that allows to have now devices, let's say for IoT, and we created what we call their zone number 8. So if we go back to near field, we split the system into devices that are up to 250 milliwatts, devices that are up to 1 watt, and we're focused on number 1 and 2 for consumer purposes, and devices that are up to 40 watts. Okay. Then on the x-axis, we looked at the next generation of power at a distance, and we've been talking about our Watt Power Hub system, which I will show you today. But we also wanted to be able to close the gap at 1 meter. Okay, so there are regions 5 and 6 that we will fill as we move forward, and that should be fairly soon. We have, and then the far field, which is in the order of hundreds of milliwatts and up to 15 feet. Now, if you look at the lower part of this slide, you will notice that by splitting the markets or this approach into near field, midfield, far field, and harvesting, it is possible to identify vertical markets. So we are focusing on looking at solutions for each one of those vertical markets. In the near field, hearables, wearables, midfield, IoT at home, smart glasses, and so on. Far field, military applications, public safety, and so on, and harvesting effectively in smart building, sensors, retail, and so on. Okay. Now, once we knew how clear that roadmap was, and we understood what customers wanted and what we needed, we looked at once more all those frequencies. We looked at the efficiency of our technology, and we built a second system. And the purpose of this second system was to try to fill the midfield approach. It was basically understanding, with the help of the SEC, if there was a way for us to go in through Part 18 and to break, and I say break in a very soft manner, find ways to push Part 18 to open up at a distance. And if you look at the transmitter in the upper figure on the left, you'll see something that looks like a wing. And a lot of you might be wondering, why is it like a wing? Why? And I'll tell you why. And then there's a receiver there that you see on the white that looks like a phone. Okay. So when we put this system together, we actually put this system together as a flat surface, a full antenna array. And we wanted to understand and make measurements of the RF fields. And we wanted to also understand, with feedback from the FCC, what it would take for us to be able to pass a Part 18 at a distance. How would we prove to them that we could actually have local power? And that's when the wing form factor comes in. We started playing with the array, and we actually ended up with a beamforming proprietary shape that eventually allowed us to have the FCC with, approve our first power at a distance certification, world's first power at a distance certification. So today it is possible to send power legally up to 1 meter here in the US. So we went to UL, we had the certification, and because there are no standards, and that was a big headache, we actually had to go and work with what's called a TCB process, which is a grant of equipment authorization. And we were able to open up, and we announced this about 3 years ago. So now that we know that we understand the technology, we put together a 900 megahertz second generation system in this particular case, and we know how to pass. The time came for us to now start basically looking at the technologies, the systems development, and being able to now build realistic devices that we could deploy, okay? So now let's get to the fun part of the presentation. Technologies and systems development. And I know I'm using a lot of time, but I go fast here. Our goal was to develop semiconductor devices and semiconductor devices for wireless power transmission. We were not looking at using off-the-shelf components, non-wireless power devices, communication devices to build this. So we looked at putting together transmitters, we looked at putting together beamforming devices, power amplifiers, receivers, and systems together, antennas, and so on. So we have built all that. And on the right-hand side, you'll see a number of reasons why, and I mentioned before. I think you can talk about improved spatial and orientation freedom as one of those features that we want to see. We want to see also a smaller devices that can be charged. I mean, coil-based devices, inductive devices have challenges in very, very narrow and small devices. So from a near field point of view, we put together with collaboration with customers, hearing aid device. I mean, and the reason I'm using this hearing aid device is it's got a funny form factor. Okay, so it is possible to build funny shaped antennas. It's not straightforward to build funny shaped coils that actually have the same gain, coupling in this particular case. We put together technologies like the module that you see on the right-hand side, which is a single PCB that includes a Energous Design 4100 and a CMOS, which is an ARM-based device, and a PA. And the nice thing about this module is that you can just deploy this in any type of transmitter and enable your transmitter by working with us and picking up the right antenna. So again, as you remember, I said we have a large library of antennas. Similarly, we looked at the receiver on the lower part. We connect our antennas. We have a 2223 CSP device, very, very tiny device. And depending on the customer's need and the power required by the product, we end up with a battery charger and management system, which today is off the shelf, but in the future should be optimized. And a BLE subsystem that comes from Dialog. Dialog Semiconductor is actually an investor in our company and a great partner to work with. Those that are engineers, I'm sure want to know how we did this. We on the right-hand side, we have the receivers. The receivers change in shape. You have behind the ear, you have in the ears. So we have the 2210, which is equivalent to a 2223 device. Those are receivers. Those are specially designed RF to DC rectifiers, okay, that have high efficiency within the parameters of CMOS technologies. They connect to a battery charger. They connect to a BLE subsystem, which could be a Dialog chip 681 or 585, and also provides power to the DSP circuitry and so on, so power to the subsystem. And remember this block, because this block doesn't change, this block stays there. The right-hand side, you have a BLE system for the audio communication. You have a 4100, which is a CPU-based system with dedicated software, and it actually provides all of the oscillation, local oscillator specific to 900 megahertz, has a preamplification RF front end that allows to now go externally to an optimized CMOS-based 3210 device. Okay, and then by using this architecture, you can have one antenna, multiple antennas, and then grow the surface of contact. So that's basically what we have on near field. We went to midfield and said to ourselves, gosh, this beamforming business is interesting, but we think we can do better than beamforming. Maybe we can come up with a new way to send power without using beamforming and still meet the parameters of the FCC. And about 6 weeks ago, we actually had the world's first wireless power system without beamforming under Part 18 certification. And you can see there once more the TCB, because there are no standards. But what's important here is that, and those of you that are communication guys that as opposed to Wi-Fi, which is 1 watt, we were able to push the conducted power to 5.5 watts. So it is possible to have a safe system at 5.5. And in the lower part, we ended up using GaN technologies. We ended up developing copper-based transmitter antennas and so on. And you can see on the left-hand side, a lot of simulation went, and these were end-to-end simulations to make sure that we were able to shape the RF in such a way that we could send as much power as possible within a constrained, localized manner. Those of you that care about the circuitry on the right-hand side, pretty much the same receivers. Now you apply this architecture to the different components that you have. You change the battery charger and PMU, depending on what your needs are for what component you want to support in the system. And on the right-hand side, as we go beyond 1 watt, we go into what we call zone 4. What we end up doing is we just replace the PAs by GaN-based PAs, which are highly effective, and then build a CMOS-based controller to provide biasing and control and other functions to the device. So that gives you an idea of, so far, how we learned what the process of, what the challenges were, what the processes were by which we designed the technology. And I want to say once more, we have dedicated devices for wireless power transmission. Finally, we can use those devices, we can play with them and build different vertical markets. If we have started with hearing aids, we work with hearables, we looked at IO trackers and smart glasses and so on. And certainly we have the power hub. So there's so many applications that it's only up to us to now continue. And what I wanted to do now is share with you a very short video. If you give me a second here. Okay. Give me a second here. Okay, so this would be, just bear with me, we're almost there.
But what a power hub is a small device that uses non-beamforming to send power to local devices that are close by. This particular design is sending power this way, but you can imagine a developer using this, applying this technology in a 360-degree angle, or perhaps off to the sides, depends on the application. But with this device, we're actually sending power to the front, and these two smartwatch designs are receiving power. One's lying flat, the other is still clasped together. Our antennas are embedded into the actual flexible material on the band. You'll see with the power levels, you're getting between 50 to 150, sometimes upwards of 200 milliwatts to each device. And the reason why is because based on where the battery is in its charge cycle, batteries want to be charged differently. Okay, as I move them out of the space, I'll kind of show you how this technology works. The LEDs get a little bit brighter as I get closer to the What Up Power Hub. You'll notice that I can spin it around. The antennas are on both sides of this remote control. So unlike coils where there's a very strict alignment, with our What Up technology, you can move and place the device pretty openly. As I move further out, you'll see that there's really no power there at that range. Moving back, putting our smart glasses there, you'll notice that it's getting an amount of power that's similar to the power levels that are received with the contact-based charging. Once again, being able to place a smart glass or similar device close to a charging transmitter, but not actually on it or not, plugging in, that's a big game changer. That's our What Up Power Hub Developer Kit.
Okay. I'm back to the presentation, and before we go into Q&A, I just want to say that I hope you guys were today motivated and have learned something about wireless power transmission. As you can tell, it is early. We're probably in the second generation of development. We are behind wireless communications by many, 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 many years. And this is a new technology that has to happen, and we need to make it happen. And I'm sure that if a small company like mine has done all this work in all these years, I'm sure that larger companies that want to focus on that will do even a better job. So having said that, I wanted to go and move into Q&A. And if there's any questions I can ask, I'm glad to do that. Thank you. Thank you for listening to me.